I can start recording now. There are 2 points that are most important concerning last lecture. The first point is that left eigenstates of the Fokker-Planck operator, or if you want, right eigenstates of the backward-Kolmogorov operator, which is the adjoint of the Fokker-Planck operator, play a central role in understanding molecular mechanisms. Sorry, understanding reaction mechanism. Of course, there's nothing specific about molecules. You can sort of apply the same concepts to any data sets in general. So yes, the first point I think it should be quite clear is that there's a prominent role of left eigenstates, and the diffusion distance between 2 points clearly exemplifies that, because what we demonstrated last time is that the diffusion distance is actually a pseudo-Euclidean distance in the space of left eigenstates. I say pseudo-Euclidean because there's this factor that depends on the eigenvalues. So the point here, of course, if the system is beautifully gapped, which is the ideal scenario we would like to take as the reference systems, in the ideal scenario, then clearly this gap enables me to truncate this sum only to the states that are below the gap and neglect this term altogether, because all terms below the gap have a factor that is basically 1, and all terms above the gap has a factor that is exponentially small, right? So in the ideal case, I really have a nonlinear mapping between configuration space and diffuse and LN space. Let me call it this way, which will end up being the diffusion map space later on. But for the moment, is the space defined by this set of coordinates. It's non-linear because these functions are non-linear function of x, right? In general. But once you have achieved this non-linear mapping, then the trade-off is that the diffusion distance is actually Euclidean in this space. And we also sort of sketched some analogy with the concept of local reference frame in general relativity, when you have sort of a locally Euclidean, or Minkowski in that case, metric of space-time embedded in a generally curved manifold of space-time. Okay. So if we want to make sense of data sets, understanding the left eigenvalues of having a handle on the left eigenvalues of the Fokker-Planck operator is a must. The second concept that sort of came through last lecture is the need for dimensional reduction. So what is the need for dimensional reduction? We already discussed. There's no hope to deal with the data set in 3n dimensions. This is by far too complicated. And it's impossible to have statistics for it. So we need to find a way to deal with this in an appropriate way. Now, of course, you have always the cheap way to do this, or sometimes called the poor man's solution, which is often the ones that you end up doing for sake of practicality. Because suppose you have you can identify the set of variables that somehow you have physical or chemical intuition that sort of drive you to think that those are really the relevant collective descriptor of your system. To give you an idea, using still my protein dynamics problem as a paradigmatic example, proteins are chains of amino acids. And maybe we are interested in the folding transition, which, I don't know, my chain assumes a very specific configuration where certain amino acids forms interactions. Typically, these interactions are hydrogen bonds, but never mind. And this is unique. Then, one important collective variables that you might obtain as a function of coordinates might be the fraction of native contact. This is called the native state, the unique state in which a protein is biologically active, and a fraction of native contact. The fraction of native contact is one possibility. It tells you more or less how much folded you are. If you are in the completely, unfolded situation, your fraction native contact is close to 0. You're in the complete native configuration. By definition, you're 1. And this is what is called a good reaction coordinate. I will deepen the concept of reaction coordinate. It's, if you want, it's the dynamical extension of an order parameter, something that distinguishes between phases. And in this case, the phases are the reactant and the product. But maybe we are interested in other collective variables, the radius of gyration, which gives you the size. Now, I will not give the precise definition of the radius of gyration, or I think I will, but it's basically the average. Is the average, I guess it's, let me do things properly, n minus 1 divided by 2, sum I lesser than j, ri rj squared. And since there are n times n minus 1 divided by 2 pairs in an n body system, right? Because of the fact that, the pair 1, 2 is the same as the pair 2, 1, and 1, 1 is not a pair, right? So this is the average distance between 2 amino acids in a chain, for instance. In this case, it's the average square distance. And it will give you, it will tell you how compact your protein is. And you can go on with other variables. For instance, proteins are not really like flexible chains, because amino acids are rigid. And what you can define is basically what are called dihedral angles. They have to do with the fact that you can rotate. It's more like you can rotate the chain around rigid axis, and you call this dihedral angle. You can define 2 per bond, and you could say like the distance could be the sum over the n dihedral angles of the distance between dihedral angles. I don't know, something like this. And we tell you, these are all collective variables that collectively represent the configuration of the chain. And you might decide that, for instance, all the information you can get can be extracted by, for instance, projecting onto subsets of variables, for instance, R versus Q, the gyration radius versus Q, and looking at equilibrium distributions in this data set. Maybe we'll find something like this. A large population here. This is a heat map now, where you see darker means that the probability is larger. maybe a large population here, and maybe an intermediate here. In this case, will tell us that the reaction has a intermediate state here, and we go there. So I can cluster now, but rather than cluster into my original space, I cluster into this space, which is basically assuming that your diffusion, you're making an approximation, and you're assuming that the square of your diffusion distance is basically, from the configuration, is a square in some subset of reaction coordinates, of order parameters, which play the role of the left eigenballs somehow, right? So you say that 2 points are close on this plane, they diffuse very fast into one another. This is really a bold assumption. This is more than an approximation, is what I would call a proxy, which is worse than an approximation. No. So an approximation is something that is meant to literally approximate another physical quantity, and ideally it corresponds to it in some limit if your model is very good, or it is a phenomenological model, but it really aims at calculating the same quantity. A proxy is more of a semantic difference, but the proxy is more like, I would like to be calculating that, I cannot, I consider this, and I hope that it's good enough to get the same information. So, right, what people really are doing, what people have been doing for decades, I would say, and sometimes are still doing, and actually I'm also doing it from time to time, is to project the data on phenomenologically predefined reaction coordinates. Obviously, there are advantages or disadvantages. The main advantage is I have physical intuition both to guide me in the choice of them and also to interpret the results. Because if I look at, for instance, if my plot was something like this, I would learn something about how my reaction goes, because I would say, hey, look, first you collapse, reducing the regeneration radius without increasing native contacts, and then you start searching in a collapse phase for the native contacts. So you see, the fact that I've used the phenomenologically interpreted order parameters bears with it the possibility of extracting human digestible information from the data. This is the physicist or chemist's more natural approach, because we've been doing this for ever, right? Essentially. What is the downside of it? Well, first of all, bad things can happen if we don't get all these local coordinates in the system in place. Let me give an example. So let's discuss downsides. Suppose we have a two-dimensional reaction on an energy landscape that is deliberately weird, something like an inverted S. Okay? And maybe let's make it a little bit like this way. This is my energy landscape, look a little bit like that. Maybe there's a barrier here, and everywhere else is mountains. Okay, here's my reactant, here's my product. So I have two states here. Now, suppose if I were to run molecular dynamics trajectories, they would sort of travel mostly along this valley. We'll spend sometimes here, then occasionally jump here, and get home. Okay? Now, suppose now I project this data onto a single variable, say the x variable. Well, since my population is large here, and here, so to say, when I project onto the x-axis and I take negative logarithm of the probability of the density, if you want to find it as a function of x, which I interpret as a free energy, right? As a divided by kT. Okay. Well, this will look something like this. There would be a minimum somewhere here and a minimum somewhere here. Okay, so it would be something like this. So if I look at this, I will conclude there are two states. One is here, where I see many configurations, and one is here when I see many configurations. But if you have a multidimensional representation, you will discover that there are more than two states, because you see there are two barriers here. There's a barrier here, and there's a barrier here. I didn't notice because I was not projecting to a sufficiently large dimensional space. And my reaction coordinate was not the ideal reaction coordinate. If I was projected on the manifold that travels along the path, so if I knew a parametrization of the red curve, and I could project beaming on the red curve, then I would be able to understand exactly how many states there are, right? But I didn't have the red core. I had a proxy of the red core that is x-axis. And the interpretation of this data set is completely wrong. Is this clear to everyone? So you see, the red curve, which at the moment I haven't really defined rigorously what it is, but I will define it in the next chapter on transition path theory. Okay, but the red curve is called the reaction coordinate. If I knew the reaction coordinate, then I can perfectly interpret the data. I can actually project it on a single dimensional manifold and get something out. But in general, I don't know the reaction coordinate beforehand. So I can only project on a set of data, hoping that this set of data is exhaustive enough to bear all the information, all the relevant information about the system. Well, I think you can sort of interpret all this in terms of information theory and information entropy. And I think in some sense what Raffaello Potestier is doing in his research line is find a way of finding essential degrees of freedom in systems that retain the maximum information entropy. But I will not digress in that direction because it's not my course. Okay? The alternative, however, is to project this onto an increasingly high dimensional system and plane provided by the left eigenmodes of the Dirac operator, of the Kolmogorov or Fokker-Planck operator. Okay? Now, what is the advantage of doing this? First of all, I know that this matters more than this, that matters more than the other, and in principle, if I can find that there is a gap, then I know exactly how many slow variables I need. And the second advantage is I'm guaranteed that I have a not a proxy, but an approximation, or even if I can approximate the L's, I get an approximation of the diffusion distance, and so maximal control on what's going on. So the advantage is theoretical accuracy, if you want. The disadvantage, however, is physical interpretation, because L1 doesn't have any simple physical meaning in terms of So if I see, if I see that my data are distributed according to some trajectory in this plane, I don't have a direct interpretation of what's going on. Basically, all I need to do is to look at each of these points, then sort of zoom them out in terms of their microscopic configuration, and then try to interpret that in terms of some collective variables if I want to extract information again. Because, you know, there's no direct interpretation in this plane. So you can't have it all. Either you have immediate physical interpretation, or you have theoretical control, or you try first to have theoretical control and then to post-interpret your data, for instance, this manifold, by projecting it into different collective variables and see how if they see any correlation between them. So I think this discussion sort of illustrates what are the challenges of the big data problem in the field of physics application to macromolecular systems, but in general to complex systems. These same problems are there for glasses, and I'm sure that if we apply them to probability distribution obtained from wave functions in quantum mechanics, we could apply the same concepts. Say you get, you know, quantum antibody problem, you get a corresponding probability density, and then you can start playing the same game of projecting in it and do whatever it takes. Okay? Okay. So in the next lectures, our attention will be devoted to finding projection mechanism into this plane, to find ways to do this. And this will be done in two main perspectives. Perspective number one is that once you have projected and you have your estimates for your L's, then you can use clustering methods based on, you know, proximal vicinity in this plane to identify the Markov state. So the first perspective is Markov state model construction. And I already have several interactions with you trying to explain to you why Markov state constructions was a relevant problem to tackle. The second reason, the second perspective I'd like to highlight with you is building what is called the diffusion map, which is more in the spirit of what you just drew, plotting the data. I tried to extract information about the curves of a reaction or what is close to what, and understanding kinetics directly by plotting the data onto the plane. There are, of course, two closely interconnected problems, but the formalism is somehow different, because in the second approach, I don't discretize the problem onto Markov state model. And the second approach, which is called the diffusion map, is a method that is actually borrowed from mathematics and is being applied to data set, even to data sets that don't come from an underlying Langevin dynamics, as a to understand when the data set has structure or when it's just unstructured. Because if your data set is completely unstructured, then your corresponding maps into the diffusion map plane would be kind of a blob with no structure. But in very interesting case, you find that as we shall see, if your data set has some intrinsic, although not directly visible structure, when you plot it on the diffusion map space, you will start seeing very nice and highly non-symmetrical figures, which are resemblant of the inner structure of the data. So there is a fascinating idea of making explicit when data have structure. And again, if you have a two-dimensional plane, we immediately see if data is structured. The problem is the high dimensionality of the data set doesn't allow us to have direct interpretation of the structuredness of the data. Okay? So this is more or less what will keep us busy for the next 2 lectures, and I'd like to stop for a moment and ask you if you have any questions. You muted? Okay, very good. So in order to do that, I will need to take a mathematical prologue. Like I said, this is a part of the theory that has been mostly developed by mathematicians. So theoretical physicists and mathematicians, of course, have enough background to deal with this. So I will not introduce any new concepts, but I will apply concepts you might know to this problem. Okay? So in particular, we will have to introduce different Hilbert spaces and concepts like that. So we consider a stochastic system defined by a Fokker-Planck equation. Now, in the following, I will omit the FP in Fokker-Planck, and I will call H dagger sometimes H backward. Okay. Now, we assume, since the system obeys the Fokker-Planck equation, we know that there is a stationary distribution, which I will denote as pi, which in the case of Langevin dynamics is, of course, the Boltzmann distribution. We have discussed this many times, right? Now, I will now use the bracket notation and define, I will work in the space of square-root integrable functions. So we consider functions that belong to L2. But I will build 2 Hilbert space out of these functions. And these 2 Hilbert spaces will vary by the definition of the inner product. Okay? Please stop me if you're all, except from Federica, who's a mathematician, the rest of this bunch is from physics, right? So you should be familiar with this concept. If for any reason you're not, just let me know, okay? So the first inner product I am interested in defining, which I will denote this way, is one in which I take my 2 functions and I multiply them and I average them with a Boltzmann distribution. And I will call the space of L2 equipped with this inner space, I will call it L2 pi, just for us to have in mind, okay? So this is a linear space of functions with this inner product. I also define another inner product, and not surprisingly, it's the inner product in which I take these 2 functions and I divide them by the Boltzmann distribution. And not surprisingly, the space of L2 equipped with this new inner product will be denoted as L2 pi to the minus 1. Does it sound okay, right? No, nothing particular particularly difficult to digest. Okay. Now, this is a mathematical prologue. In mathematics, sometimes you don't need to motivate why you go from one to another line of your proof, why you consider certain mathematical objects. You have total freedom to do whatever you want as long as you follow the rule of logics, right? So what I will be doing now is introducing these concepts apparently without a particular reason, but then I will go into applications, and all of these concepts will be related to another and will give me the opportunity to approximate the left eigenmodes of the Fokker-Planck operator. Okay, so don't be disoriented if you see that I jump from Hilbert spaces to operators with no apparent physical threading line. The physical application and the logic behind introducing this concept will become clear in, say, shortly. Okay, so the next thing that I'm gonna do is to introduce two operators that act on different Hilbert spaces. Actually, one operator is the propagating operator, and the propagating operator is nothing but the time evolution operator of the Fokker-Planck equation. So what is it? If you want, its definition is given any distribution. I won't call it P, I will call it rho now to avoid confusion between the propagating operator and the probability density. And the action of this would be given by the following intuitive equation. Take rho of x at time t and propagate it forward according to the Fokker-Planck equation by an amount t. Sorry, yeah, that's correct, absolutely correct. Okay, but this is the Green's function of the Fokker-Planck operator. It's the propagator. So if you want, on an operator sense, I think it's clear to you that this is an operator equation. And this follows directly from the fact that the function P obeys the Fokker-Planck operator. Basically, this is a Fokker-Planck equation. This is a solution of the Fokker-Planck equation, right? A formal solution of the Fokker-Planck equation in operator sense. Everybody's convinced, right? Now, note, we know that the Fokker-Planck dynamics is not Hermitian, right? Not unitary, and the Fokker-Planck operator is not Hermitian. However, this propagator is Hermitian in one of the Hilbert spaces that we defined. So note that P is Hermitian in L2 pi minus 1. How do I prove it? Well, in the following way. I get my V vector P U in the inner product pi minus 1. This is equal to integral in dy V of y 1 over pi of y. Remember, this is the definition of the inner product, times the integral in dx P of y t plus 2 x t plus 2. Yes, there's a x here, there's a y here, this is correct, and of course there's an xt here, and then I get a u of x. Now, the next step is to use detailed balance. And remember, detailed balance means pi x p from x to y is equal pi y p from y to x, right? So if you apply it here, you can actually swap x and y at the price of adding a particular combination of pi's. And in particular, this is actually equal to dy v of y integral in dx p xt plus 2 yt u of x divided by pi of x. Which in the end turns out to be nothing but p v u in pi to the minus 1. Okay, so this is an important property of the, why do we care about this being Hermitian? Because it tells us something that we knew already, but it tells us basically that its spectrum is real and the eigenmodes are real. Because up to a Boltzmann factor, which is real, we have an Hermitian operator implying real spectrum and all that. Okay? We knew it already for the Fokker-Planck equation, but it's another way of, so basically all these properties are already inheriting the fact that I have an explicit transformation from the Fokker-Planck equation to the Schrödinger equation. But the mathematicians normally don't see that as a very clearly, not because they are not smart enough, but simply because they don't see the Schrödinger equation, or they don't give the same importance to the Schrödinger equation that we do, because of course for them it's just another equation. Okay? Now, let's do the same with the transition operator. So let me remind you, the transition operator was defined Did I define to you the transition operator already? I think so, right? Anyway, the transition operator, let me redefine it for a moment. I first propagate and then divide by Boltzmann. And I multiply by the Boltzmann factor, and this is an integral over y, of course. So you see what I do here in the transition operator t tau. I am multiplying and divided by Boltzmann factor. I multiplied inside the integral and taking it away outside the integral. It looks like this is a very, so while the propagating operator is very natural object, because it's basically the time evolution operator of my dynamics, the transfer operator, sorry, not the transition operator, the transfer operator, I'm using the transfer operator that is defined by this equation, looks like a pretty artificial object. I guess we would all agree that why should I ever be interested in such an object? Why should I multiply my distribution by pi Well, already multiplying to distribution is something that, we don't do very comfortably, but these are multiplicative distributions. There's nothing, it's not like multiplying to delta functions here. These are really densities, right? So already, why should we multiply and take out these terms? Now, the reason will become clear in a moment. And when we will discover that basically the transfer operator is the evolution operator associated with the backward Kolmogorov operator, as I will demonstrate. So clearly, now you begin to see why they're important, because the evolution operator and the backward Kolmogorov operator share the same spectrum, because HB commutes with e to the negative HB, right? Implying same spectrum. And same set of eigenstates. So the transfer operator is actually the main person of interest for us. Okay, of course, I have to prove to you that this is true. Okay? Okay, let's do so. Well, to show this, we note that if rho of xt is a solution of the Fokker-Planck equation, then u xt, which is the rho of xt divided by Boltzmann, is a solution of the adjoint equation. We know this, right? We have been discussing this several times. It's simply to say that the right eigenmodes, from the right eigenmodes, I can get the left eigenmodes, taking the right eigenmodes and taking away the Boltzmann factor, right? So that's all I'm saying here. Well, then, I can use this equation and propagate forward my u function. So I can build a propagator. Let me provisorily call it t tilde, and let it be e to the negative eb tau. And all I know is that my t tilde will propagate forward in time my u function. Right? But then, if you write this in terms of the Kolmogorov-Chapman equation, like in this case here, with a p, and you remember the relationship between U and rho, then you arrive exactly to conclude that d tilde is actually the transfer operator. So the point here is these two operators are interesting, and of course, there must be a way to go from one to the other through the usual transformation, because one is the time evolution operator of the forward Kolmogorov, and the other one is the time evolution operator of the backward Kolmogorov. And in fact, in the notes, and I think I wouldn't like to go too much into this proof because it's quite trivial, is that you can define a multiplicative operator M, which goes from pi minus 1 to pi, and it works like this. M acting on rho of x will be pi of x rho of x. So basically you're multiplying by the Boltzmann factor, and then, you know, I'm gonna go fast here because it's not so important. But if you apply the transfer operator to my rho function, then you can write this in terms of the M function with the M operator. I can use the M operator here and say that this is actually P x t plus tau y t, M acting on rho, which is actually M to the minus 1, which is this, integral dy p x t plus tau y of t m rho y, which basically has tell me the following important identity: m to the minus 1 p m, which is another way of saying, if you want, this is another way of proving that the transfer operator is operationally written as the propagator of the backward Kolmogorov equation. But again, this implies that T of R and P of R have the same spectrum. And their eigenmodes, eigenstates, sorry, are related. How do we see that? Well, let's suppose I know the eigenstates, let me call it Li, lambda I of the transfer operator, which is what we actually want to compute. Then I can write n to the negative 1 PR m Li equals Li, lambda I, because of the identity I just demonstrated. Well, then I can multiply by m and I get P m Li equals lambda I m Li, where I wrote this term here. So I get these are the right eigenstates, or the eigenstates of the propagator. And so all I've proven is that I have the same eigenvalues, lambda I, and that the left eigenstates, once again, are given by the right eigenstates the n-1, the right eigenstates, which is what we've always been saying. So this is all to say this operator are really what we're interested in. And if we can get a handle of a transfer operator, if we can get the eigenvalues of a transfer operator, we have both the left and right eigenvalues of the Fokker-Planck equation. So the transfer operator is really what we are interested in. Okay? Okay. End of the mathematical prologue. Let us use these concepts and show you how you can use them to get an estimate of the left eigenstates. Okay? So I will be assuming from here on that sampling the dynamics and reaching ergodicity is not a thing. It's not an issue. I will leave aside the sampling problem. In real life, sometimes I don't even know how to sample. So basically, what I would be assuming is that I can perform long enough simulations to sample the equilibrium distribution. Okay. So the idea is to consider the following object. Let me call it GF as a function of tau. And this is the matrix element of the transfer operator according to the L space, L pi, L2 pi space. So if I look at this and I write it explicitly, I find the following thing. Now, when I write these expressions, I often interchange between this notation and this notation whenever the time t is not used in any other part of the equation. And the reason I can do that is that if the system is Markovian, whatever happens between t and t plus delta t is the same that would have happened from 0 to t unless there's an explicit time-dependent force. Say you have a changing magnetic field in my system with a given schedule, in which case, of course, you're violating microscopic reversibility because you're telling that, remember the discussion on the second principle of thermodynamics. If you have an external force, you violate microscopic reversibility. So we are assuming the system is macroscopically reversible and Markovian, which means that I never have to worry. Sometimes I use this t because it enters in the equation. I want to give it explicit. Some other times I don't need it, and I just remove it, like in this case, okay? I'm just saying evolving in time for a time delta tau or tau. So why do I want to consider this particular matrix element? I mean, there's nothing particularly interested in it. Well, because it's very simple to compute. So using central limit theorem, you can see that GF of tau is actually 1 over n. I have n trajectories, or n times along my trajectories. So basically, what I'm doing, I'm taking my time series, that's my x of k. I'm selecting a time tk, and I'm correlating the function f evaluated on the trajectory at the distance tau, and I'm repeating this for, oh, shoot. Sorry. And I'm repeating this for n different times. You see, this is t, sorry. This is tau, this is tau, this is tau, and I'm averaging all this. So this, if you go back on the definition we had here, if my trajectory is sampled from an equilibrium distribution, really this is the probability, this is the time correlation function of the f function, because this will give me the probability to find the function f of y at time 0, and this will give me the associated probability of finding it at f of x at a later time, and this will connect the two by Langevin dynamics. So a way to compute this thing is through this average when I take n to infinity by central limit theorem. So this is really a time autocorrelation function of the function n, of the function f. Okay, that's a nice curiosity, but why should I bother? So, gigantic so what seems to be boiling down here. However, there's an interesting observation to make. That if I choose this to be an eigenstate of the transfer operator, I'm using the small letter. Well, then, well, it is immediate to show that this is actually simply a lie of tau, lambda I of tau, sorry. So this, the autocorrelation function of a specific function, the eigenstates of the transfer operator, is actually the associated eigenvalue. Okay, not very useful. Now comes the point where all this becomes useful. So let's assume we have found a proxy of L I tau, which, now using the function notation, this is a function. And let's call it this function L tilde, which is an approximation for L tau I of x. Because in real life, we don't know. And this is what we guess. So basically, what I'm going to tell you is something very, very close to variational approximation, Ritz variational approximation in quantum mechanics. Remember, in quantum mechanics, you would like to solve the Schrodinger equation. You cannot. You guess a wave function, and then you use Ritz variational theorem that tells you that, whatever you do with an incorrect or suboptimal wave function will give you an upper bound of the ground state energy. And if I get a better estimate, my upper bound will lower, and I will get closer to the right energy. This gives me a powerful tool to improve on my approximation by varying the parameters in such a way that I can lower the ground state energy in quantum mechanics. Now, I want to build a similar concept here so that I can start from a proxy of the left eigenmodes and systematically build better and better approximation that ultimately lead to my variational estimate of the left modes. Is that clear? So in order to do that, of course, I need to prove it, but I want to make a request. I assume I can choose L, my proxy, to be orthogonal to the ground state. And this is actually trivial. It looks like this is a very abstract request, but if I write this quite clearly, this means I do this. Now, remember, what is L naught of x? Who tells me what is this?
1.
1. So I can take it away. So all I'm asking is I have a mean-free estimator. How do I build a mean-free estimator? I take any estimator. Let me call it my precursor estimator. I don't know. Let me call it psi I of x. And then I build L tilde I as psi I of x negative the Boltzmann average of psi I of x. And if you do this, then you're guaranteed that you satisfy this condition because you're explicitly building a mean-free object. You're taking away the mean. So of course, if I take away the mean, after that, I get something that is mean-free. Okay? So this is to say that this condition that I chose to add is not something that is difficult to implement. It's simply something, it's like the normalization condition, something I can do. It requires solving an integral or sampling for sufficiently many points, but it's not something that poses algorithmic challenges. Well then, and here comes the statement, G of my proxy will be lower than lambda tau v, lambda 1. The first non-vanishing eigenmode. Well, first of all, let me remind you that the lambdas, the eigenstates of these are expressed as, I don't know, but these are the eigenmodes of the Fokker-Planck operator, right? Because of the backward, why? Because if you remember, t is e to the negative backward t, and backward Kolmogorov and forward Kolmogorov have the same spectrum, right? So the eigenmodes of the transfer operator can be written in this form, where these are the eigenmodes of the backward Kolmogorov, which are the same as the eigenmodes of the Fokker-Planck operator. So this tells me that lambda naught is 1, and that any lambda 1 is smaller than lambda naught, the lambda 2 is smaller than lambda 1, and so on and so forth. So if the lambda are not, and then they grow, the eigenmodes of the Fokker-Planck operators start from 0 and then build up. The lambda I start from 1 and go to 0. Simply because of this relationship here. So going back, now the variational principle works in the opposite direction, because the largest lambda corresponds to the smaller eigenvalues of the Fokker-Planck operator. So in this sense, is perfectly analog to the Ritz variational principle. The fact that you have a different inequality simply comes from the fact that these small lambda are negative exponent of the eigenvalues of the operator. Okay, so what I found is that if I have a proxy, then I can control the quality of this proxy by this variational condition. And then I am basically a turn, because I can do exactly what is done in Ritz variational principle. I take my proxy and I expand it into a truncated basis of the exact eigenmodes that I don't know, of course. Suppose I'm interested in the first. In the first state, I can do this for many, but let's say I take the first eigenmode and I expand it, then G L tilde 1 of 2 is equal to sum over I and J Ci Cj Li 2 transfer operator L to J relative to pi. This is sum over Ij Ci Cj lambda I2 delta Ij. Of course, I can take away this sum. I get sum over I Ci square lambda It. Now, each of these is smaller than lambda 1, so I can take and say I can bound this by lambda 1 to sum of I Ci square. And if I have chosen the largest basis, and if I choose a complete basis, this is 1. And therefore, I got my inequality. Which complete the proof. I've proven this relationship here. Okay, so with all this in hand, we can finally show how can you actually use all this mathematical formalism to build a proxy of my states. Okay? So we chose a set of functions these are my trial functions. And for the moment, For the moment, let's assume we can choose them to be orthogonal. Now, guessing a state of orthogonal function relative to this inner product is by far something easy to do. Because if you write that explicitly, it really means that you're thinking, I know exactly what this integral is doing. But again, if you write this in terms of a ergodic trajectory, this is the average over each point of your ergodic trajectory. And basically, this assumption means I am able to find n functions that are completely uncorrelated. So clearly, I've stated what I would like to have, but it is not simple to find uncorrelated function. For instance, let's go back to the example of the radius of gyration versus the native contact fraction. Clearly, they are not uncorrelated because typically the native proteins are compact and therefore have a small radius of gyration. So if I look at what is the probability of observing a certain value of high native contact configurations, I can certainly find correlation with the low gyration radius. Not perfect correlation, because there exist compact configurations that are non-native, but certainly all native configurations are compact. So for most cases, I am dealing with correlated guess function, trial function, and I have to deal with that. And I will deal with that at the very last. Okay? But for the time being, for the sake of argument, let me first assume they are not correlated, because this will make the proof simpler. Then I can build the following matrix, which is the representation of my transfer operator in these spaces, right? Exactly like you would do in quantum mechanics. You're familiar with a variational approach in quantum mechanics, right?
Yes.
So you would recognize that this is like doing H and M equal N, H, M, where M is a trial space. Okay? And then what would you do? You would diagonalize this and then try to minimize the ground state energy, right? So that's exactly what we're going to do here. We build this object, which is, of course, is trial, and I put a tilde to remember them. Now, in general, this is expected to be Hermitian, right, in this Hilbert space. But typically, whenever you deal with final statistics, properties like hermiticity are not exactly satisfied because they are satisfied on average. So that means that if you anytime you diagonalize something, you get like complex eigenvalues, and the average value of the complex, the imaginary part, goes to 0, and which is not very good numerically. So the better thing to do is to take your matrix that is in general not a time correlation function, that is not necessarily symmetric, as you would expect from microscopic reversibility. Remember, this is a time correlation function. So microscopic reversibility implies that this function must be symmetric, right? However, it is symmetric after you've done an infinite average. And you don't do an infinite average, that means that you will always have a residual non-symmetric part, which will always introduce complex parts in the spectrum, which you don't want. So the best thing to do is to diagonalize it, to take this matrix and to symmetrize it by hand. So, going back, first you guess the set of states. You try to have them uncorrelated as possible. And then you subtract the average for each of these functions, say the duration radius, the fraction of native contact, whatever, to make it mean-free. Then once you have this set of trial function, you build your proxy. And what do? You evaluate this matrix element. How do you do it in practice? You go back to this definition here. Evaluating that matrix element essentially means evaluating the time correlation function, which means take your stochastic trajectories, compute the value of K1 here, compute the value of K2 here, and take the product K1 and K2, plus then do it at a later time, K1 and then K2, then do it at a later time, K1 and K2, sum all of this, take the average, and that's for time tau, okay? So that's how you in practice estimate this matrix here. So from simulations, you can get this matrix. And once you have this matrix, you can, of course, diagonalize it. You can symmetrize it. And once you have symmetrized it, you can easily diagonalize it. So we can easily go forward and get an expression, sum over n, t tilde, n m, big M equals lambda tilde and bn. And then clearly this means that my proxy in this basis, my proxy of the nth eigenstate is the linear combination B n, where n refers to the nth state of chi there's a typo in the notes, never mind. Okay, how do I know if my choice of trial function was good? So how good is this? I approximate. I try a slightly different one, which will give slightly different coefficients, and then whichever will have the smallest first eigenvalue will be the best one. Okay? So this provides a scheme to get a variational approximation for the left eigenmodes. Now, the last thing that remains to be discussed is that we always assume these very strong assumptions of no correlation between the trial functions. Let's now assume that there is a correlation, which means that we can build this matrix element that is non-trivial, is non-diagonal. Right? This is, if this was in the assumptions that we've done before, this is the identity, or the Kronecker delta, if you want. Well, let's now assume that this is not a Kronecker delta. Then, from the linear algebra theory, it turns out that you can still arrive to the similar equation, but now you have to solve a generalized eigenvalue problem, which is one in which on the left-hand side you have your tilde n m bm, But on the right hand side, you have to pre-multiply by this function. So, to conclude, and then we'll go back to this and discuss it again next lecture to make sure that we got the important points of this long discussion in place. But let me summarize it before we close. We understood that much of the dataset understanding problem is hidden in getting a handle on the left eigenmodes of the Fokker-Planck operator, or equivalently, the eigenmodes of the transfer operator. Now, from the mathematical point of view, there are the same functions, but from the practical point of view, evaluating the left eigenmodes of the Fokker-Planck operation is something you cannot do for almost any system, while there is a way to stochastically estimate in a variational scheme the eigenfunctions of the transfer operator, which are the same eigenfunctions. And the reason is that basically we can build a correlation function that is a time correlation function. So we can build the autocorrelation function, which is the matrix elements of the transfer operator, in terms of a time correlation function. Sorry, where is it? We have it written here. So the time correlation function can be evaluated from simulation. So from simulation, we can obtain matrix element, if you want, in some functional space, in some functional basis of the transfer operator. So what we did was to show that there was a variational bound, which allows me to ultimately assess the quality of whatever I'm doing in terms of how good is my proxy, my approximation. And then basically what we did was defining a way that started from a guess of the left eigenmodes, ultimately lead you to a matrix you can compute from simulations, and then to a generalized eigenvalue problem, which will give me my proxy of the left eigenmodes. And I can control the quality of this proxy by the variational bound. So this provides a practical scheme to organizing the data. Next lecture, I will show you how you go from here to Markov state model construction, for instance, and how much can you learn about a system as complicated as a folding protein by applying these seemingly abstract mathematical concepts. So you see, the field of biophysics, traditionally a field for people who don't like mathematics but still want to do physics. I know somebody would be very angry to hear this, but I would say it's a fair statement overall. Historically, is now merging with advanced mathematics, or so to say, stochastic mathematics at least, and theoretical physics. And the result is that quite a lot of inherently hard problems that could only be solved phenomenologically with the proxy and coordinates and collective variables guessed phenomenologically can now formulate it in a rigorous sense. And all that I'm telling you is taking place now. So this is what I called a revolution in statistical computing, at least as far as the application to biophysics, because this systematization of a originally very, very phenomenological field is happening in this decade. So we are more or less in the phase when, before there were some experiment by Ampere and by Gauss and by Coulomb, and all of a sudden came Maxwell and was able to build an elegant mathematical way of presenting the same information in a form that is rigorous, making sense, and therefore powerful, because it allows you at that point to make predictions using mathematical methods. So now this is what I define to be well, not me, but many define to be the statistical computing revolution we are experiencing these days. Okay? So, and part of the reason why I decided to focus on this more and more over the years in my course, as this revolution becomes a fact, not just a fashion. Okay? Well, all revolutions are fashions, of course. Okay, enough. I have another meeting. I have to skip lunch. So, ci vediamo martedì. Vi metto online le note aggiornate entro oggi e entro domani le 2 lezioni questa settimana.
Perfetto, grazie.
Grazie.
Arrivederci.
Arrivederci.